Good morning or afternoon, whenever you tune into this. Um, Hopefully you've had a very nice holiday. I know I did. Um, but back to some maths. So last term we spent the last week and a half or 2 weeks looking at different types of transformations, and one of them was enlargements. So I thought this topic of similar triangles fit very nicely into doing afterwards, because to find that to know that two triangles are similar, we've got just kind of two criteria. It's essentially that one is an enlargement of the other. So if we look at this B, we can see that this triangle here is 2, 2 and 3 centimetres, and the triangle to its right hand side is 4, 4 and 6 centimetres. Hopefully you can quickly spot that every length has just been times by 2. And we say that that has a scale factor of 2. Hopefully you remember when we were writing out the descriptions of a enlargement, we were saying enlarged by scale factor, blah blah blah, and then we said a centre. And that's all similar triangles are. They are shapes that have the same scale factor of length, so they're all multiplied by the same number. So if you're asked to prove if a triangle's congruent, see if you can get from one shape to the other by multiplying by the same number. The other property we have in a similar triangle, like in part A, is that all the angles are the same. If the angles inside the triangles change, they are not similar anymore because they aren't just an enlargement. If we make triangles bigger and bigger, so if I draw this triangle here, if I take a different colour and just enlarge this triangle from the same spot, you see I'm making it larger and I'm making that larger. Can we see this angle here is not changed? And we could make that argument for all sides, and if we were to connect this up, we would find that these angles are the same and those angles are the same. That's because these lines would be parallel, and we would have some special angle rules there. That would be an F angle or a corresponding angle, and we'd have the same going here as well. And on this one down here, this would still be similar. All they've done is flipped the triangle, and you're not always going to see it drawn nicely for you in questions. All they've done is flipped it round. So imagine if we tipped this triangle over like this. So the 30 was there, the 45 was there, and the 105 was there. It's got the same angles. At this stage, we don't care if they're the same lengths. We don't need to know that. We know they're similar because they can have different lengths. By having the same angles, we know that to get from this triangle to this triangle, we times by the same number each time. And then this one, well, we can see we've got a scale factor of 3 looking at these two sides, and the angle between them is the same. So therefore, we know that this length must also have that scale factor of 3 from this side to this side. That's a bit more of a special case. Generally, you just look out for, can I multiply by the same number, or do they have the same angles? If we have a look at actually answering some questions, so within the foundation paper, it's just required about finding missing lengths. If you do any searching online, there's also similar shapes, properties for areas and volumes, but that's when it goes to grades 6s and 7s. So make sure you're not spending time trying to understand that stuff when we don't need to. But we need to find these two missing lengths. So our first step in a similar triangle problem is you need to find a pair of sides. And what I mean by that is two lengths that show the same spot on the shape. So this shows this right hand side slant, this also shows this right hand side slant. And that's how we're going to find our scale factor. Sometimes it's just really easy to spot. Sometimes you need to do a division with your calculator. But with this one, it's pretty easy to show that that is a scale factor of 2. If you were wanting to find, if it was a bit more difficult numbers, you would do the large length divided by the short length. And as you can see on that triangle, if we did 10 divided by 5, we would get the scale factor of 2. But that's a good way to remember it if you are, if you've not got nice numbers. And then you need to, well, there's 2 criteria. If we're going from small to large, then we times by the scale factor. And if we're going from large to small, we divide by the scale factor. And that would be my final step up there. And that makes sense. If we're going from a small shape to a large shape, we would expect the length to be bigger. And if we're going from the larger shape to the smaller shape, we would expect the lengths to be smaller. So in this case, we are going from the small shape to the large shape. So I'm going to times by my scale factor. So that would be 8. And I'm going to times by my scale factor. So that is 14. The different part on this one is that, well, they've drawn the shape out not perfectly linked up. We can see that the triple line angle and the triple line angle are both in the bottom left. The double line and the double line are both in the bottom right, etc. In this case, it is not. So I'm going to draw out the shapes again. And I'm going to draw them out so they are in the same orientation. So I'm going to keep this one the same. So I'm going to draw that out with the double lined angle in the bottom left. You won't always get the line notation, sometimes you'll get a number there. And then I'm going to draw this one out with the double line in the bottom left. So the triangles can look the same, it doesn't need to be drawn perfectly. They should be looking the same anyway, because they're similar. And just get your lengths in the right spot. So 4 centimeters goes between the double lined one and the single lined angle. That would be here. 6 centimeters goes between the double lined angle and the triple lined angle. So that is 6. Again, if you've just got numbers there, let's say like 40 degrees, 30 degrees, you just need to think, well, 6 goes between the 30 and 40. Where are they on my diagram? And then we've got a blank here. So let's find our pair of sides. So let's go through step 1. Well, my pair of sides, 5 links up with a blank, 6 links up with a blank, it's 10 links up with 4. So to find my scale factor, I can do 10 divided by 4, which is 2.5. 2.5. So therefore, to get from my small shape to my large shape, I need to times by my scale factor. So 6 times by 2.5, 6 times by 2 is 12, half of that is 3, so add that on, 15. And then to get from my large shape to my small shape, I need to divide by my scale factor. So 5 divided by 2.5, that is 2. So then if we go back to our shape and just fill in where they wanted it to be. So 2 and 15 there. A very common type of similar triangle isn't where they'll have the 2 triangles separated, but they'll have a contained triangle. And at first it's a bit more confusing about how do we have 2 triangles from this. But the first step is to find your 2 triangles and draw them out. It's very simple once you see me do it once. So your first triangle is going to be here, what I've drawn in red, so I'm going to draw that out. And that's going to be my small triangle. That's got a length of 7.5, that's got a length of 9, and that's got a length of 6. And then my second triangle is going to be the full triangle. And hopefully you're looking at the one on the right and you're starting to think, oh yeah, I can spot where the 2 triangles are coming from now. So if I draw that out, that's got a length of 8. This has got a length of 9 plus this box. So right now, maybe I'll just write it like that. And then this has got a length of 7.5 plus whatever that extra length is. You'll not always get the full information with these, but you will always have enough information to answer the question. So let's find my pair of sides. Well, the pair I have, without any missing boxes or anything, are these bottom ones. So my scale factor, or SF, as I like to write it, that's going to be the large side divided by the short side, so 8 divided by 6. I mean, and you can leave that as a fraction, 4/3. I probably would in this case, because if I actually did 8 divided by 6, I'm going to get 1.333333. And if we round that too early, we're going to make some mistakes. If you don't like working with fractions, give yourself at least 5 decimal places, and then you're not going to get any rounding errors in there. So I need to then think, well, this is my small shape, this is my large shape. So I'm always going to be timesing in this question, actually. To get from this length to this length, I'm going to times by 4/3. So let's do that. 7.5 times by 4/3. Let me just do that on my calculator. That's going to get me 10. So 7.5 times 4/3 equals 10. But what's my box going to be? Well, if this full length is 10 and this is 7.5, then this must be 2.5. And always watch out for that, because that's a very common thing, that the number you get from the multiply isn't actually the final answer. And then to get from 9 to this missing length, we need to do 4/3 times by 9. And that's going to get me 12. So that full length is 12. So the box I'm after is 3, because 9 plus 3 gives me 12. Okay, maybe you want to pause the video and have a go at this one now, and then I'll go through it afterwards. Okay, hopefully you've had a go at this one, and I'll go through it now so you can check your answer. So my first triangle is going to come from this top right angled triangle. So that's going to look like this. We're going to have a length of 6, 8 and 10. And they've actually done this question well, because if you did Pythagoras of 6 and 8 you would get 10. Trust me, there are practice questions that don't do a proper right angle triangle, and it annoys me. And then my next triangle is here. So I'll draw that out in blue. That's a length of 9, they've given us that. We don't know this length, and this is a length of 10 plus something. So hopefully the pair you spotted was from 9 and 6, so my scale factor is 9 divided by 6, which is 3/2, or 1.5. You can have it as any of them. You don't even need to simplify it if it's a calculator question, because you can just type that in your calculator, can't you? So to get from here to here, I'm going to times by my scale factor, because I am going from small to large. I'll write that in the middle there, small and large. So 8 times by 1.5, that is going to give me 12. So this length here is 12. And then 10 times by 1.5, that would get me 15. So therefore this box is 5, because that full length would be 15. So hopefully you got them. And then one final question to look at. This is where it gets a bit harder, and you can see that this was on a 2019 paper, and it was question 20. So it was right towards the back end. It's only 3 marks, but that's still a decent amount of marks to be able to do with these questions. And the more difficult thing with this is that there's these two triangles in a bit of a hourglass or sand type of shape, and the angles link up in a bit of a strange way. So if I draw out the bottom triangle separately, we've got E, D and C. So this is a length of 20. All of this here isn't important because they've drawn that on the shape for us. What we can spot is we know that these two angles are the same because they're vertically opposite. And the common mistake people make, they think that these two angles link up. And they think that these two angles link up. But that is not the case. And I'll show why it's not the case. If we consider our Z angles, or alternate angles is what we should remember them by, we can see through alternate angles, because these lines are parallel, they've drawn these arrows on to show they're parallel, these two angles link up. So the angle by A and the angle by D link up. And then by a similar argument, we have that these two angles link up. So it's actually the opposite side angles that link up in this case. So if I was to redraw this triangle at the top, ABC, well, I know it's going to look like this with C there, but I need to get this the right way around. A links up with D. So if D's in the bottom right, A must be in the bottom right. And B links up with E. So if E is in the bottom left, B is in the bottom left. Then I can start to fill in my lengths. That's 8 on the bottom. A to C is 4.8. So A to C is 4.8. And then B to C is 6.4. So therefore I'll put that between B and C. This is my small shape. This is my large shape. So we're wanting to find out the length of BE. BE goes from BC and then CE. So what I want to do is I want to find this length here. Then I'm going to add these two together to find the full length of BE. So let's work to find CE to start with. So find my pair of sides. That's going to come from this bottom. So my scale factor is 20 over 8. That gets me 2.5. So I'm going from my small to my large. So to get from 6.4, which is CB, to this length of CE, I need to times by 2.5. So 6.4 times 2.5. That gets me 16. Nice number. So this length here is 16. And I can draw that onto my original diagram. So C to E is 16. So therefore, going from B to E, that includes the 6.4 and the 16. So therefore, BE equals to 16 plus 6.4, which is 22.4 centimeters. So that's kind of as hard as it gets with just a finding lengths type of problem. They can always throw it in and involve other different skills to make it even harder. But as a standalone question, that's as hard as it's going to get. So there'll be some practice questions for you, and let me know if you are needing any help. Hopefully you stuck around till the end.